So, I don't know.
So now I have to pay.
Yep, $600 or something. For nothing.
So start 95.
Oh, $700 for nothing.
How are you?
Good.
Bon appetit. Do we expect anyone else?
I don't know.
So
I think
maybe
Sam's
down.
still coming, isn't he?
Huh?
I think Sam's still coming, isn't he?
Okay. Who else? Oh, Diane. Yes, they important. And so we are in the CHEM767. It is meeting number 22, and I do not think that we have any administrative comments. You just chill, chat, discuss. In brief, there are two goals for today: socialize and multiply two matrices. Socialize meaning talking about motivations, goals, and expected results in the course. Not just
I was like, how are we gonna socialize?
right.
Are we gonna play games? Are we gonna play Mafia?
We'll need to play a game with ma'am.
So there will be much more talking than deriving, but derivation will be very boring and, as Levi suggested, the word mind-numbing.
Yes.
Again. So the only thing that we need to do analytically is to multiply two 4x4 matrices, and probably we'll split the load. But there will be very important positive consequences and benefits. So administratively, no classes next week. Material Research Society conference, where many of you are going. It will be not much reason to.
Are you going? There's two.
Where is I'm going?
It's 3 out of
7.
6 now.
It's maybe not majority, but substantial part.
Close to
Where is it?
Phoenix.
And when we'll come from the conference, we'll decide whether we have steam for any presentation of the projects or we just take easy. Well, let's discuss it later. Now it's well, maybe easy projects, maybe nothing. Maybe just one or two labs. Scientifically, we do have new chapter. Let's see, number 5. So, relaxation, meaning you can sit and relax. So, we are going to cover benefits, structure of the next sections, give some examples for noisy bath. Then we should cover the standard deviation connection, STD deviation connected to autocorrelation function that was introduced by Aaron. And then we need to multiply L times L, where L is not angular momentum but Liouville operator. And then we will analyze it, and then our time will be done, will be complete. Well, maybe if there will be more time, I will just bring up the figures from our yesterday lab. Fix. So today I know the answer on the question who we are and what we are doing here. I do have a guess how to answer this question myself. So some of you are already involved in academic research related to relaxational phenomena, like non-adiabatic charge transfer, and some of you phonon-induced relaxation. You are either involved or can be involved in the near future, or maybe you already have some results and you are working on publication. So what we do in class will not literally help to complete your research, because you spend like 20 to 40 hours per week for your research, and in class we just maybe 1 hour per week just chatting. But we can provide a little auxiliary help in the following aspect. Suppose you have all your results in looking for like charge transfer, electron dynamics or exciton dynamics, and you have written a nice paper that is has enough results. Suppose that your advisor doesn't have time to take your results and write a paper for you, so that you need to do everything yourself. Then suppose that you need to write the methodology section, which you can easily cut and paste from previous papers or textbook. This is not a problem. But then you submit it to the reviewer, to the editor, and typically it comes back with a request for revision with some arguments like, I do not believe that this approximation is valid. I have a suspicion that this can be done differently. And then you have an active interaction with reviewer. You need to argue, and you need to have more general idea about the background and fundamentals of the theory that may be not in the straightforward procedure that you are following. And what we are doing here in class, I have a humble hope that it may help in this aspect. So it equips you for being competitive in fighting reviewers. So it is not, you cannot prepare and have the ready recipe. Like, I don't care what they ask, I will answer this and it will be always correct. It will not work, but it just gives a sense of possible deviations from the central path and how one can look on this class of problems from different angle. I hope it was sufficient for motivation. What have we done in this class in previous several meetings? What was our major pathway? How do you see it?
Describing spin states?
It is correct, but one can describe spin states with Hamiltonian formalism, like with wave functions. Spin states are our guinea pig.
Non-equilibrium.
Yes, yes. So we are trying to develop a framework in which we can efficiently describe non-equilibrium phenomena. And the major challenge that prevents us from sitting in our comfort zone and using wave function is that wave function doesn't survive when we apply average over ensemble. Well, one can do average over ensemble based on wave function, but then one still needs to find probabilities or expectation values, and it is not a wave function anymore. So we are leaning towards either Heisenberg equation of motion for expectation values, observables, or two density metrics, because these pathways, this direction, these tools are okay. They survive if we apply average over ensemble to them. This is one of the major take-home message from whatever we did in, let's say, previous 5 meetings. Another practical skill that by now we know for sure how to describe time evolution of the quantum system that is perturbed by external force, which can be like permanent oscillating harmonic oscillation by electric field or something like that. Not bad. Then we do know how to do very simple average over an ensemble to take into account the diagonal disorder, inhomogeneous broadening, the fact that we have multiple replicas of the same system with slightly different frequencies. And this approach allowed us to describe free induction decay and photon echo, right? But in these approaches, we are still staying within the major lie of basic quantum theory. Like if you teach quantum mechanics to the like students who take it for the first time, or if you remember yourself taking it, there was one of the postulate statements: if the system is excited into some specific state, it will stay there forever. Which is a lie. We know that everything will relax to the ground state. Well, to be safe, people add the keyword isolated system, meaning it doesn't interact with anything. But this is also a lie because there are no isolated systems. So and even if we perform an average over inhomogeneous broadening over several replicas of the system, they still are isolated in a sense that they do not dissipate energy. We still do not have relaxation. And each of the systems, when we turn off the external field, stay in the state we did prepare it. It may accumulate phase, but it doesn't change the occupation numbers. Enough. We need to depart from this point. We need to allow system to lose population, to approach thermal equilibrium. This is our goal for next couple of meetings. Relax and achieve thermal equilibrium. A black humor joke. Doctor, what's the temperature of the patient? It's okay, it's a room temperature. Or maybe a medical doctor asks a nurse, "Nurse, can you measure, is the patient okay? What is the temperature? Measure the body temperature." And nurse answers, "No problem, it's okay. It's a room temperature."
Meaning he's dead.
Yeah. So we are, not we, the systems that we are describing approaching thermal equilibrium in whatever we looking forward.
And decomposition has not occurred yet.
What if the room's 98.6 degrees Fahrenheit?
So how can we approach
It is when you are
how can we approach this goal, and what are our small technical sub-goals? How do we, like, we cannot be too general, like describe relaxation, so what? How do we start? We need divide and conquer, very, very little steps. Well, you do remember that phenomenological, we do have you remember that we do have Bloch equation, or we do have its analog in the, we can derive its analog in the language of density metrics that shows that in addition to accumulation of phase, which is rotation along equator, and excitations and de-excitations due to external field, which is in optical will be transition dipole times electric field. In addition, there are relaxation terms, so there are minus terms. So everything after this point represents oscillations, everything before this point represents relaxation. So we can phenomenologically postulate that based on a common sense, everything relaxes, and we can feed it with constants. The longitudinal along the magnetic field, if we talk about magnetic, and transversal T2, T1, T2. So T1 and T2 constants that take into account all these complicated phenomena. Interaction with gas, relaxation, and in many cases one can just feed them to experiment or borrow them from the literature. But if you are starting description of a new system, then you may want to find them. And in some sense, the goal of our meetings is to find microscopic, or maybe even add to mystic way to calculate T1 and T2. So if you know how to do it, then we can describe relaxation in any system.
Is that supposed to be d by dt of s of y?
X
S
D D
y.
D D D S Y, yes.
You just have dt dt.
So goes 1 to,
No, this shouldn't be.
yeah.
So how do we approach it? We still have several things to chat and discuss in general. It's more ideas rather than derivations. So why? I don't know, it sounds silly to myself. I even cannot pronounce the questions. Why system is not isolated? Why any quantum object relaxes? I've heard, you know, the if you try to make up an explanation which is not an explanation, just logically it is nothing, but it is just words, one can tell us it is a demagogy. So so I can say system relaxes because it is what they do. But we need to do microscopic, to find microscopic reasons. Any ideas?
Didn't you say that there's always a quantum vibration or something?
Yes, yes. Very good, very good. This is a good reason. So the main microscopic mechanism that we will catch by the like 2 or 3 weeks from now is when there is a transfer of excitation from one quantum system to another one, from the primary system, like our toy model for two-level system, to one of the systems in this environment. And this process can go into several channels, and when we look for their constructive interference, it will go smooth relaxation, very similar to Fermi's golden rule. But adding quantum description right away is too quick. Let's go slowly but surely and see if relaxation can be introduced, even if we are considering an analog of QMMM, when our primary system is quantum and everything around is molecular. Molecular mechanics. Everything around is classical. So there were a lot of efforts to prove that relaxation is a consequence of noise. How do you like this verbal formula? So because background radiation or maybe substrate and solvent exert some random noise, and there is some non-zero interaction with the system, this random noise may lead to relaxation. Let's try to explore this hypothesis as our first step, and whatever we get, success or failure, then we will use some developments and experience from this modeling to more detailed quantum modeling. So we are done with benefits. Sections. What will be, which sections we can cover or will be reasonable to cover? Noisy bus, quantum bus, noisy B, quantum B, then aspects of quantum algebra of operators and commutations for this relaxation mutations, and then detailed balance principle. So the way how we reach thermal equilibrium, detailed balance. So it is approximately 4 sections, maybe 1 meeting each. And today we are looking on the noisy buff, which is quantum classical or semi-classical model, where our primary system is quantum and the whatever makes it to approach equilibrium is classical. So how can we rationalize in our heads the noisy path? We do not, right now, we do not need to develop exact models. There will be time to be literal, rigorous, and exact, but we need to come into peace with our own mind and get a general idea how we can model influence of environment, where the noise is coming from. So one reason is what Levi has mentioned, that our two-level system of given frequency interacts with a mode of environment which will be, can be electromagnetic field or phonon mode. They have some interaction, and there is a little frequency offset. So it interacts with one, it interacts with another one, it interacts with the third one. And if you take into account that each of these modes perform classical motion with different phase and different amplitude, it will be sufficient noise exerted onto the system. Can we rationalize it in any other models? How can we just design simple model that will result in noisy influence of the surrounding on the model?
Could you do like a collision?
Yes! Oh! I do not know how you come to this mind reading level. Yes, very good, very good. Super. So, let me interpret the thought of Levi, which came really at a good time. So, suppose we have a gas of, let's say, diatomic molecules. One molecule is special because it is in the excited state. And all other models are not special because they are in the ground state. And then, if two molecules come into close vicinity, they may exchange excitation through some interactions. But we do not know how closely they come to each other, or how far they come to each other, and how long they stay in the vicinity. So it could be scattering, like coming here and then reflecting one way, coming there and then reflecting backwards, coming nearby and then slightly deviating. So they are staying in the interaction regime for short time, right? And each of them interact with our primary interest molecule for limited amount of time. Okay? So even if we apply all machinery that we developed before, like rotating frame so that Hamiltonian will be time independent, the phase for their interaction will be always the same, and it will start over for each molecule that comes again and again. So if we will set up the analog of radio frequency that drives the transitions between ground and excited, and we take into account influence of each of surrounding molecules. We know that when they come to the closest proximity, there is a maximal value of this intensity of their interaction. But if they come for shorter time, or if they're not touching each other, it can be smaller, and it will be different phases. So this is typical time they stay nearby. It can be a little longer or a little shorter, and the offset of this value from zero approximately shows how closely they come. So this is an amplitude, and if we return back into from rotating frame into the Schrödinger picture, it means that we need to dress it by cosine. So interaction Hamiltonian equals times cosine omega t. So if you bring back fast oscillations, we can do them here. And at this point, we change the phase and change amplitude. At this point, we change the phase and change amplitude. At this point, we change the phase and change amplitude. So it will be same leading frequency of the perturbation. We can stay within the approximation of slowly changing Hamiltonian. We still can use the concept of Rabi frequency. But the phase and amplitude will be randomly changing, which means it is a noisy environment. Of course, one can develop a microscopic model and maybe do molecular dynamics and look for each individual molecule, when it comes, how long it stays. But we can tell in average that in average the molecules stay in vicinity this much time, correlation time. And it will be sufficient to develop qualitatively correct consequences.
So if tau c from like Anna's presentation, if that is within like the autocorrelation, will it fail or will it still be fine?
The autocorrelation function is a mathematical tool to characterize properties of random functions. Random meaning stochastic, randomly changing functions. It's a very good tool to characterize them. Depending on details, so one can guess very many brands, very many sorts of noise. And depending on the sort of noise, one may want to convolute, jam together, consolidate this long, complicated function into something that we can analyze simply. So this is why we need autocorrelation functions. Make sense? I'm very happy. So we do have an example of noisy bus. Okay? And Levi has a talent to either ask right questions at the right time or guess the right words at the right time. So if you want to characterize these functions, we can notice several properties. So suppose that our noise is affecting, it is off-diagonal noise in the Hamiltonian, which is, well, in the interaction picture, it will be only perturbation. Or if this Hamiltonian should be energy, then each parcel. So if we have diagonal elements correspond to offset between the driving field frequency and main transition of the quantum system. If we have distribution of these diagonal terms, you have diagonal disorder, and it may correspond to inhomogeneous broadening and dephasing and photon echo, right? Now we are considering what if we have disorder in this Rabi frequency, if they are slowly changing in a random way. Slowly changing meaning changing the amplitude and phase. Now, how can we characterize this random function? mathematically, how do you characterize a function if you want to convolute it into a single number of a couple of numbers? You do expectation values, momenta. For example, one can do integral t capital, one over t capital. Let's see what it will be average value of this random function. If it is really random fluctuations above the central point, then you get either central value or in most cases you will get zero. Right? At least in the way how we describe it, it will be if the number of positive initial phase and negative initial phase is equal, it will come to zero. What else? This will be the same all the time. But we believe that it will affect our dynamics. What else can we, how can we characterize this function? I know who knows the answer.
Fourier transform.
Yes,
Kind of.
but this is the next higher level. Something really simple. Simplest. When I was taking undergraduates, it was during the first month of the first semester in the analysis of experimental data. If you have random data,
Linear regression, least squares analysis.
oh yes, but it is still too very smart. Something really simple. Like there is a
Square.
central value and standard deviation.
Oh,
So you can just take this omega square minus expectation value square. Right? How do you call it? STD? Something wrong?
no, that's it.
That's it.
STD also stands for sexually transmitted disease.
Oh, let's skip it. Yeah, not in this area. So, will it be zero or it will be different from zero?
Unless it's like not random. You should.
Well, if
Zero.
it will be zero only if the function is zero. Otherwise, positive and negative, it will always give positive contribution to this STD. And it is a good measure of randomness, or quantitative measure of this random function. But it doesn't. It still doesn't show, and it doesn't tell anything about this correlation time. So, what if we take this value not at the same time, but slightly offset? If you take the same procedure as for standard deviation, but we take one function explored at let's say time 0 tau plus t, and another at time t. So meaning that you shift your function along time axis a little bit and compare it with itself. If it will be constant, then nothing changes. But if it is a decaying function or this randomly changing function, then such overlap will decay really quick. So we need to and we can call it just ACF of tau. See, one time is integrated over, and second stay as parameter. So if the function is long correlated, then this ACF function will show some long time dynamics. And if it is long correlated, and if it is short correlated, then this ACF function will drop rapidly, and then will be very close to zero. So one can approximately tell that for short correlated functions it is delta function. Or it can be some finite width function with where it stays non-zero for the period of time that is exactly this correlation time. Okay, it was like boring mathematical details, but where is the physics? How do we get an opportunity to drive system from excited state to the ground state? So the idea is that if we have randomly changing phase and amplitude of this radio oscillations, and we perform an average over ensemble of such trajectories, then the population will decrease. I do not know any more of intuitive arguments, rather than to do a little math. So if we take the L superoperator and apply it towards the equation of motion for density matrix. If we will simply average each term in the equation, simply add together each term of the equation based on the different representatives of an ensemble, we will get nothing. Because these oscillating terms in the first power will cancel each other. In average, they fluctuate up and down, and in average, they do nothing to the population. So when first order is insufficient. So one will need to go to the second order, and we will find a way to do it. Before we go to this mathematical detail, I want to bring in just one more philosophical concept. And I hope you find it useful. So we do have a hypothesis that randomly oscillating driving field does induce relaxation. In order to inspect this relaxation, we need to perform propagation of density matrix in time, propagate, and then do average over ensemble, where this psi index stands for different elements of an ensemble. Rho average, summation over elements of ensemble, and here it depends on time. And then this density matrix that has been averaged over ensemble will show the relaxation. So what we do here is propagate plus average. And this is literal way to take into account relaxation induced by noise. On the other hand, one can follow, I wouldn't say smart, they all are smart, but efficient, optimal way. Optimal. When one can immediately formulate an equation of motion for density matrix that has been already averaged over an ensemble. Right now we can do simple tests and try this little approach, but then we are going to find equation of motion for this object and avoid averaging. If you want to be precise, one needs several replicas in an ensemble. Like yesterday in the lab, infinite number of ensemble representatives was done with infinity equals 40. If you want to get some competitive publishable, you get like several hundreds, 300-500 elements in the ensemble. And it takes time. Not too many, but still does. But what if we avoid this literal, straightforward way and derive some equations that will represent in average the influence of an ensemble on the density matrix that is already this averaged one? Does it make sense?
How do we get the averaged one initially?
We do some tricks. We just guess that we are already dealing with the one that is averaged. And then we find that there will be terms in the equation of motion, special new terms in the equation of motion that are contributed by the interaction with noisy environment. I'm so happy to find a way to pronounce it. Very good. Where are we now?
We're multiplying the movable.
Okay, yes, optimal way. So, new terms to equation of motion originating from noisy environment. Good. So if we are looking onto rho at time t plus delta t, we can tell that it was rho at t multiplied by L of t. T plus this. So what it was before times delta t. Good? Increment. And we already know that if we do an average of such construction, we will get 0 because our noise is symmetric. What if we look for the rho of t plus 2 delta t? Well, we should write approximate because it is series. So it will be rho of t plus L of t times delta t times rho of t plus L of t plus delta t times L of t times delta t squared times rho of t. Do you believe it? No objections? So we are doing just finite difference propagation of the density matrix equation of motion. And we have the intuitive expectations that first term will be insufficient. We need to go to the second term in this expansion. So this gives us the reason that for population decay, a second power of Liouville operator, a product of two Liouville operators, one after another, which can be also considered as how would you say it? Yeah. In quantum field theory, if you have diagrams with two interactions, like first term one interaction, second term two interaction, and then we go to the rest. So two instances of interaction subsequently coming one after another. Something like this. One interaction at time t, another interaction times t plus delta t. Oh, no.
Two body.
Oh, well, it's just second order. It's two interactions with the
Second order.
second order.
Second order type.
So we will work out the details in more rigor later. But now the main reason that we have a great hope that second order, the square of the Liouville operator, will give non-zero contribution for population relaxation. So we will look just on the product of these two operators, and later on we will work out how to average it along the noisy environment. Okay? So the major thing that I'm going to do is to take
Screenshots.
this Liouville operator for two-level system which derives propagation of density matrix, and take this matrix square and just analyze how will it look like and whether it will prompt us some specific type of dynamics. And I suggest this pathway because it is the quickest way to get some insight. Otherwise, in all other ways, it is longer durations. Right now, if it is only first power, it brings the accumulation of phase and transitions between ground and excited, and migration of non-zero values between diagonal and off-diagonal. Let's see what we will get if we multiply this matrix by itself and just see the second order contribution. I'm going to make a screenshot of this panel, then erase everything and work out the matrix multiplication. Simon Aaron did avoid the great joy of matrix multiplication, but I'm so happy that there are at least 4 of you here.
So we can all do about
4 elements each, like 4 rows, 4 columns.
Yes, so we can all do one.
Yes, so that difference.
A 4x4.
16 operations.
No. 64 multiplications.
No, but it's divided by 4.
And here we are done with standard. We are done with standard deviation, and we have left the multiplication of matrices. I'm going first to practice calligraphy and rewrite it so that we see it all together, one by one, and then can apply this row by column rule. 0 times 0. So it looks like the omega capital goes in a circle and signs are flipping, plus minus, plus minus. Like zeros, and here is plus and minus offset.
It's not the complex conjugate, it's not the Hermitian conjugate of the...
No.
Usually in second order diagrams you have something time it's Hermitian conjugate.
No, here it is the same evolution, infinitesimal evolution, applied twice.
I thought that the omega was divided by 2.
Yes,
Okay.
it will be more reasonable to keep this divide by 2 notation rather than redefine omega. Yes, let's keep it. Although the final conclusion will not.
Or we could just multiply by 2. And then only have
No, well,
Divide the whole
or we can forget about it now and work it out if we need exact answer.
No, if you times I of delta H by 2,
Then,
and then divide the
divide the
entire
whole thing
matrix by
by-
1/2, then
So
you only have to do 2
so
times.
just putting factor 2 here and
Factor 1/2 there.
yes, good. That's a good suggestion. Actually, 1/4.
Yeah.
Shoot, did I mark myself? Do I have any mark here?
So let's split available space onto this 16 cells, and then practice row by column rule. So the first one, 0, I times I is minus and another minus plus omega square. Another omega square, right? Then next, same row by next column. 0 plus 2 delta h bar omega plus 0 plus 0. Right? Zero minus omega square.
Why?
Because you got,
Why isn't it 0?
No, this one. I do here.
Oh.
Wrong.
oh yeah.
Okay. First element is still 0. Second is 0. Third is I times I minus, another minus, so it will be plus delta H R 2 omega. And the last one is 0. Correct? Only 3 spots, so we will do less cells. Let's just split a little.
Which one, last one or this one?
Just do a couple of elements.
No, we already did it
Do
for,
this one.
yeah.
We didn't finish the last one.
Last one will be minus 2 omega square.
This one with this one.
Oh, I see, yeah, you're right.
0 minus
Oh, that's supposed to be easy.
1
No, 0.
no, last one is the, no?
You're timesing,
Oh, sorry, I wasn't here.
0.
This one, okay.
No,
Wait,
just
you need to do row by column.
Yeah. This one with this one
0.
is 0. Yeah.
Okay.
This one with this one.
So you have one term?
Yeah.
Okay.
Seems like.
Please keep going.
Okay. This one 0,
Oh, you're going by the column. Okay.
0. Plus I. Oh, you have I, right?
I, yes.
So now this
Minus
is
times
here.
minus plus I times I minus.
Yeah, it's good.
That will be minus
Minus
2 delta over h bar times omega.
so,
Can you do one more?
so this one is going to 0 minus I minus omega
Squared.
minus
Omega squared.
plus minus
The last column.
0.
Okay, good.
Both are minus, right?
Yeah.
Yes. Very good. Many thanks.
It's easiest call. Think so.
I want to do the last column. Now the internal ones are going to screw me up.
There is some symmetry. By doing this much elements, one can guess the rest.
Right. I can see it.
Wait, I think I, no, it's,
Which one are you doing?
Oh, wait, no. No, I'm used to doing it, but yeah, so here.
Third row by second column. So you've got -2 on the square, right?
Yeah.
Okay, good, good, good.
I'll go to the last one. You the last one? You're closer. I'll just go up and do the last one. I'm just kidding.
I guess the last one will be easier.
Okay, you can have the rest. It's easier for me to keep track of what all of them. But
Just
you can
find
do
the
what you want,
symmetry and write it.
because I'm gonna make some mistakes. I'm gonna switch up my stuff a little bit. Are you sure you
Okay,
won't be upset if I
yeah,
do the last
okay.
one?
Yeah, whoever.
You're discussing
Yeah.
who is going to be last.
It's just confusing.
The inside ones are easier.
Second
I
row
think.
is third column.
No, wait,
Those are right, there's more zeros.
my brain is used to doing it in like the same, same. So, I go like initially then some.
Is it positive?
Okay.
It's just that.
I omegas times I.
Oh, sorry, yeah, I.
Yes, yes.
Oh, yeah.
Plus 0.
Yes.
No, are you?
Plus 0.
Yes.
Plus.
I omega minus.
Good. Next one.
Alright.
Minus omega squared. It's minus omega squared.
Mm-hmm. It's gonna be 0 next.
Plus 0.
Plus.
Second row by
minus.
second column.
So this is gives you I times I minus 4 delta square over a bar square.
Uh-huh. And plus omega square from the list. Yes, times this. I times I is
Plus
minus.
omega square.
Yeah, good. And then the fourth row by third column.
0 plus 0 minus 2 omega delta h bar
Isn't let's try 0.
minus
Isn't it 0?
Do this like this. Zero. Good, thank you. You can pass it.
Now find the symmetry when.
oh sorry some people just avoided the zeros and did all the math.
Levi avoided the 0, yeah.
I figured why write 0.
They're on.
Wait, why do you have divide by 2? There shouldn't be a divide by 2.
What's this?
Maybe multiply.
That's
No, forget about it.
nothing.
This isn't divided by 2?
No. Because we brought the 2
We
out.
brought the 2.
Oh, so that goes away.
Like, let's put 1 over
Okay.
4.
Okay, so this one goes away too then, right?
Yeah,
And then it repeats again.
yeah, so you can
Two
just do
omega
2
squared.
omega squared.
Yep, it's done.
Oh, yeah.
So let's rewrite it. Let me rewrite it once again in no.
So I guess I didn't have the easy one.
Yeah. It's all symmetric.
So let's rewrite this matrix once again, and let's rewrite it in the situation after we perform an average over noise. We agreed before that. Oh, I just erased it. Average of the first power of omega, if the omega is time dependent and noisy, we'll get 0. So each term where we get omega, not omega squared, we can safely erase it. There, here, and there. So here, L squared is related to matrix where it will be plus 2 omega squared, 0, 0, minus 2 omega squared, 0, omega squared minus 4 delta
Omega squared.
right? Minus 2 omega squared, 0, minus 2 omega squared, 2 omega squared minus 4 omega squared minus 2 omega squared minus 2 omega squared.
Is
You
h bar
forgot you were
squared.
h bar squared.
Right? Good. Thank you for keeping a good eye.
Now just same as the other.
Erase everything except.
Yeah, he did. I did mine in parentheses. Dayan did his in not parentheses.
So we are doing, well, let's put bar symbol. Well, you've developed rigorous notation later, but we assume that we are performing average over noisy environment. And what is important? Which terms should we look at? So this operator is applied in order to get the delta rho in time. So it is delta rho 1 1, delta rho 1 2, delta rho 2 1, delta rho 2 2. So we are mostly interested in the terms that affect change in the first and last terms, which correspond to population. So we do see that we need to take care of signs. I see something is missed. In the final result, the plus and minus should be flipped, but we will not find it in this short time. But I just know the right answer. But what is correct? What we've got for sure? What is a positive result of this exercise? That we have obtained non-zero elements in these 4 corners. They determine the change in time of the population terms. So they couple how population terms depend on their previous values. So the still place here this symbol of average. Then standard deviation, the average measure of the disorder for this noisy environment, is responsible for change in population, for change in the first and last elements, for elements of density matrix that correspond to occupation. They also somewhat affect the off-diagonal elements. But the dephasing that we have considered before performs much stronger influence of the off-diagonal elements. Typically, this term is smaller than dephasing. To be precise, we can take into account this block too, but it is of the secondary importance. What is really good, what is really important, that we've got terms that operate change in time of population. How can you formulate? Standard deviation measure of the noisy environment determines change in diagonal elements of density matrix. So it is change in population and a mechanistic way to show approach to thermal equilibrium. Change in population and mechanistic way to approach thermal equilibrium. Does it make sense as a general direction for future exercise? Any objections in the, do you see any logical, anything is missed in the logic? Or more or less it is reasonable? So I interpret that you tell maybe something is wrong, but I haven't found it yet. So we are going to pursue the same approach with more details and more rigor. But the general idea, even if you go from noisy classical environment to purely quantum environment, the general trends will be the same. First order interaction Hamiltonian or whatever, Liouvillean operator upon average over ensemble gives no contribution to population change. Therefore, we need to go to the next term. And in the next term, the expectation value, the average characteristic of the level of noise or level of thermal excitation of the quantum bath is responsible for the rate of energy dissipation from our primary system. If we will look onto our modeling that we did in the lab, then we can observe some trends where we pursue the literal inspection of the dynamics. So we are doing modeling of photoexcitation system from ground to excited state. So the blue is population of excited state, red is population of ground, and those are off-diagonal elements. And as time passes by, this stays in the excited in case we do not have noisy environment. If we apply the random noise added together to the driving field, to whatever was our laser field in this modeling, this red line still has the pi pulse that promotes system from ground to excited at specific time, but then there are these background noise contributions. And if you look onto a single trajectory, it has some deviation from 100% population, but it is random and looks like a noise. But if we repeat the same modeling with an average over ensemble of such trajectories, where each of the trajectories experience different realization of the noise pattern, then this thick blue line shows continuous decrease with a more or less constant rate. So one can fit it into a single exponential, and basically one can write down a very simple equation of motion for the density matrix that has been averaged over ensemble. And instead of this ensemble average, there will be just one constant that shows constant decay. And if we increase the level of noise, the relaxation goes quicker. And just to have the better picture, we can remove visualization of each element of an ensemble and just look on the occupation as function of time upon the average. There still there is some level of noise because the number of elements in the ensemble was small. If we do it from 40 to 400, it will be a very smooth color, even if the noise is really random. Do we need to discuss anything else? I think it is enough. So let me announce the completion of the meeting number 22. I wish you, those who travel, happy travel to the Material Research Society conference. And if not, just have a happy time investing your efforts into other activities, projects, or fun. Happy Easter break. And we are going off record.